went 33-3 against the Bills. That was sad. We kind of owned our frankness.
All right, did everyone pick up a review packet for the calculator portion? So this is what we're going to do, adjusting the calendar a little bit here. We are, initially I had the calculator test being on Wednesday. Now I'm going to move it to Friday. So we'll still have 2 full days, today and tomorrow, to practice those types of problems. It's going to be 3 FRQs, and we're going to just cycle through them over the course of these next 2 days. Now, Wednesday, I do need to start the next unit, and Thursday as well, but I will spend the second half of class to continue reviewing. So I guess technically we still have 4 days before our test, but I do need to cover some of the new topics. Okay. Now there is homework for the new 2 sections, Wednesday, Thursday, but I'll check both of these on Monday. Okay, so I want you guys to focus your attention on preparing for the Friday portion test.
Those 2 are for the next unit.
I'm sorry?
Wednesday, the topics are for the next unit.
That's right. These are for the next unit, right? So I didn't want to lose instruction days, but I wanted to also give you additional time to feel ready. Yeah, quiz next week, right? So right, we need to. But these aren't too bad. We just have to memorize or remember the rules, and it's just a couple of rules. So I think we'll be ready for the quiz. I will have help sessions starting on Wednesday. So Wednesday morning, Thursday morning, and Friday morning. I'll send out a reminder. It's on the board there, but I'll send out a reminder on over text. All right, you're going to need your calculators. Preferably, you have 83 or 84. But we can also get away with 36 Pro. It's just a little bit more tedious. You can't see the graph. You have to rely on the table of values. Okay. Yeah. All right. I do want to point out that on page 19 of your packet, I do have some guide in terms of calling some of these features in the calculator. So we'll practice them. We'll review them, and I'll go over how those keystrokes are going to be used from both calculators' perspective. Okay, so let's start with number 1 here. All right, so particle moves along the y-axis. So just think that, here this particle is either moving up or down, and it can only do 3 things. It can only stay in at rest, or it can move up, or it can move down. Okay, so moving up would mean positive velocity. Moving down would be negative velocity. Okay, v of t is given by t sine t squared for t is greater than or equal to 0. In which direction is the particle moving at time t equals 1.5? So what do you think we can do to figure out which direction is moving? Just by, yeah, good. Insert 1.5 into the function. And if we get a positive, we know positive velocity means moving up. Negative velocity would mean moving down. Okay. So we can just plug this directly in into your calculator, but I also want to show you a different, another way to All right, so what we're going to do is obviously you can just plug this in, plug 1.5 in for t, and insert all that. But we can, if we save it under y1, then we can continue to recall it without having to type everything in all over again. But first, make sure when you go to mode, make sure that you're in radian mode. Okay, next up, under y1, I'm going to have you type in that function. Now, the calculator can only handle the variable x. So on paper, you're going to write t, but in your calculator, it can only handle x. So don't try to force your calculator into a different variable. It'll start complaining. So just always use x in your calculator. So here I'm going to use x sine of x squared. Okay. So now we're going to go back to your home screen. So you're going to do second mode. Second mode will take you back to your home screen. Some of your calculators may not have this, but if you do, this is a nice one. If you do, let me double check. Yeah, so if you do alpha trace, you're going to have a menu of values of y1 to y9 that you can call. You don't have to, yeah, so it's easier to get to it if you do second trace. And here we have our function stored under y1. So if you hit enter on y1, and then now I'm going to do parentheses 1.5. So now what it's going to do, the calculator is going to replace every t in your calculator or every x in your calculator with 1.5, and it's just going to type that. This is going to evaluate it for you rather than you having to type in 1.5 in for the expression every time. If you can't get to it using that menu, then you're going to do vars, yvars, function y1. So I'll write on the board here. Okay, so I got 1.167. So we can say v of 1.5 equals and since v of 1.5 is greater than 0, we know our particle is moving up. Oh, it is. Let's see. Okay, now part B, it says find the acceleration of time t equals 1.5. So how can we get to acceleration from velocity? We got to take the what? Derivative, okay. But the nice thing is, I mean, if we went through derivative, we can do it by hand. We have to go through product rule, and then after product rule, we can plug in 1.5. The nice thing about the calculator is that the calculator can evaluate the derivative for us at a point. So to get there, you're going to say math 8. You can hit the number 8, or you can scroll down to number 8. There's an end deriv feature there on there. So math 8. You're not going to write any of this down on a test or on the AP exam. This is not going to mean anything for the graders. But I just want to just write this out so that you know where to get to that. You're going to do math 8 end deriv. And also, you're not going to write that end deriv on your on paper. You're going to say that means v prime of 1.5, right? Or a of 1.5. Right. Acceleration is v prime. So if you do math 8 there's that feature that's going to show up, and basically we're just going to ask the calculator to find the derivative of a function at a particular point. You're going to say d over dx. You're going to type in, you can type in x sine x squared, or because we've already stored that function under y1, if you do alpha trace, you can just call that y1 and save yourself a little bit of time. So, and then x at 1.5. Now, what this means is that we're asking the calculator to find the derivative of this function and plug in 1.5 at the same time. So it's evaluating v prime of 1.5. So what we're getting is actually the acceleration of this particle at 1.5 seconds.
Oh, when you do the map A, it doesn't.
Right, it's a little bit different. Yours is going to be an older one, so you're going to type in the function, comma, x, comma, the number. So this is an example here. So you'll type in x sine x squared, comma, x, comma, 1.5. Okay. I took the 1.5 for that. Why? Yeah, for some reason it doesn't like that square outside, so just make sure you put it inside. So they thank you.
Straight.
Mhm.
Did the enter the x sine x squared x. He got me. It says error argument. Yeah.
It needs to be, there needs to be comma between each of those things. So right here, it's the expression comma x comma the value. Okay, so I got negative 2.049. So this is a negative acceleration. So what can we answer about this here? It says, is the velocity of the particle increasing at t equals 1.5? So if we're asking for velocity increasing, do you guys remember from first semester, what does that mean? Is it asking about velocity or is it asking for about something else?
Because that's where acceleration.
Yeah, ask for acceleration. So this means that if velocity is increasing, my acceleration should be what?
Yeah.
Positive, right? But here, because we get a negative acceleration, that means the velocity of the particle is really what? Decreasing. Yeah. So we can say since v prime is negative 2.049, we can say that velocity is decreasing. Okay, I want to show you, this is a first theorem rearranging of values. It says, given that y of t is the position of the particle at time t, and that y of 0 equals 3, find y of 2. So I'm going to rearrange first theorem for us. First theorem says that if I take the antiderivative of an expression, it'll make it rise up to the antiderivative, and I can plug in the upper and lower bound. If I rearrange that, we have something called this here. I can say the final position that I'm looking for is equal to the initial position plus displacement. So what that means is if I am looking for an ending location, as long as I have some starting location that the problem gives me, I can just figure out how much progress I've made from that starting location. Okay. So in this case, I'm trying to find y of 2. I know y of 0, which I'm going to replace that in a second. And I'm trying to figure out how much progress have I made, or this particle has made in that 2-second interval. So I can say the integral from 0 to 2 of v of t. So displacement is how much progress that I've made if I were to take all the velocities and accumulate those velocity over a period of time. So this is going to give me displacement. Okay. How much ground did I cover? Okay. Now, this is also something that we can do in the calculator. Our calculator can also do definite integrals. Our calculator cannot do indefinite integrals, but it can do definite integrals. So to get there, you're going to do math 9. So math 8 will evaluate the derivative for you. Math 9 will will do a definite integral for you. So if we do math, if you scroll down to 9, or you can just do math 9, there's a FN integral, FNINT. Okay. So we're going to type this in. We're going to say 0 to 2 of my velocity function. And again, if you do alpha trace, you can call that y1 that we've been storing this whole time dx. So the definite integral of velocity will give us, between 2 points, will give us the displacement. Okay, 0.826. So now what we can say is my position at y of 2 is I'm starting at location 3 because y of 0 is 3. And then between 0 and 2 seconds, I made 0.8268 progress in terms of movement. Right, so if you're on the calculator, you're still going to do FN integral here, but there's going to be 4 arguments. You're going to type in the expression, comma x, comma lower bound, comma upper bound. Yeah, so there's an example that you can see on the board there. Okay, part D, find the total distance. So total distance and displacement are similar. Displacement is how much progress you've made from where you started. Total distance is adding up any forward and backward movement that you're making. Okay, so accumulating. So if you move 3 steps forward and 2 steps back, that's counting as 5 rather than 1 foot progress. So total distance formula looks like this. It's the definite integral from 0 to 2 of the absolute value of v of t. So to get there, again, you're going to do math 9 to get to f an integral. You're going to say 0 to 2. And then inside your integral notation, you're going to put the absolute value. So the absolute value is under math number ABS. Math number ABS. I'll put that over here. And then once I'm inside the absolute value bars, I can go ahead and put in y1, which is storing my velocity function, dx. Okay. It may take a little bit more time for it to evaluate. Now, if you're using a 36 Pro, you can also get to the derivative feature, integral feature. It's all stored under, you see in blue here, there's that d over dx. So if you do second d over dx, it'll have that same math print feature as the graphing calculator. So you'll type in the expression here, the full x sine x squared, and then comma x equals 1.5. And then if you want to get to the definite integral feature, it's right below on that first column. There's that definite integral feature. Do second definite integral, and then you're just type in 0, 2, and the expression. And if you want to get to the absolute value feature, it's stored under math number as well, same as graphing calculator, math number ABS. Okay, do you guys get 1.173? Right, so these are the major features in terms of the calculator parts of the calculator. The calculator portion for involving calculus. So being able to use the end derivative feature, being able to use the f and integral feature, and then if total distance and location is included, then we use these two to find them accordingly. Okay, so I just want to introduce them to you. We'll have a couple of days to kind of practice and get comfortable with it, but these are the things we need to be able to do. Okay. All right, let's look at number 2. Number 2, we have a table of values. It says temperature in degrees Celsius of the water in the pond is a differentiable function. So differentiable function, that just means it's a smooth curve. No sharp turns, no holes, no asymptotes. So we can be assured that there's not going to be any place on the graph that is unexpected. It's all going to be a smooth curve in between. The table shows the water temperature as recorded every 3 days over a 15-day period. So that means on the 0th day, they test the water temperature of the water is 20 degrees Celsius. The 3rd day, they test again, 31 degrees. 6th day, 28 degrees. Okay, so on and so forth, all the way to the 15th day. And so all the, not a lot of data, and it's all spread out. Okay. It says part A says use the data from the table to approximate W prime of 12. Okay. Now let's talk about this. W prime of 12. What does that notation represent?
12th day.
Okay, but what does that prime represent? Okay, so we say derivative, right? We say W prime of 12, but you're right. It's talking about how fast the temperature is changing on the 12th day. Okay, I'm going to write those words there. Derivative, rate of change. Those are the things that we think of. Now it says approximate. So we can't find the exact slope at 12 because we don't have a function to find the derivative for and plug in 12. But what's related to derivative? What's something on the algebra side of things? Derivative is related to what? That again? Slope, right? That's this algebra way of describing derivative is slope. Now we can do slope without calculus, right? So slope is just what? What's the formula for slope? Yep, change in y over change in x. So we can do that, right? We can do change in temperature over the change in time on the 12th day. So if we want to find slope, what do we need to find slope? 2 points. What 2 points would you choose? So the key thing here is you want to choose the closest 2 points to 12. So so there's a couple of options, right? We can either choose what? Yeah, we can choose these two, or we can choose these two here.
And be more accurate.
Well, the thing is, they don't specify which one because, yeah, you're right. It doesn't specify. So this problem can accept multiple answers. And there's one more option that's acceptable. What other 2 points could we choose? What do you think?
22, 21.
I'm sorry?
22 and 21, right?
Yeah, so we can choose these two. That's one option. We can choose these two. That's one option. There's one more option. Yeah, we can all choose these two. So they're all, and we definitely want to be around here, right? Anything that's further away is not as accurate, right? So in terms of, the question is, how accurate can we be? The best we can do is just choose points closest to our source, right? And anything further away is not as accurate.
And that.
It's up for debate, right? But at least you've chosen something that's within range, so they're all, if they ask you in that case, any of those will be fine. So we're going to say W prime of 12. I'm just going to choose one. I'm going to use squiggly line to indicate that it's obviously not entirely accurate. We don't know the exact rate of change at 12. We just know that we can choose 2 points and give our rate. So I'm going to choose the last two here. But you can also choose the other two options. I'll say W of 15 minus W of 12 over 15 minus 12. So I'm going to find the temperature change between those 2 days divided by the change in the number of days. So 15 is 21 degrees. 12th day is 22 degrees. Okay, what's our unit of measure here? Degrees Celsius per day. Yep. So we look at our units, right? So numerator is in terms of Celsius temperature. Denominator is in terms of time. We just put those two units over each other. So how would you phrase this in a way that where you can describe what's going on?
Well, the temperature is decreasing by -1/3.
Right, good. So on the 12th day, we can approximate based off of our limited data that the temperature in the pond is decreasing by this amount on that day. Okay, good.
Also, it's like by the time you get to the 12th.
On the 12th day. Yeah, on the 12th day. But obviously it's not entirely accurate because, we have all this data that's spread out across multiple days. But the best we can do is any of these 3 order pairs. All right, so part B, it says approximate the average temperature in degrees Celsius of the water in the time interval from 0 to 15 days using trapezoid approximation with subintervals of length delta t equals 3 days. So that means the width of 3 days. All right. Average temperature. What does that remind you of? There's something that we learned recently. Average value. Okay. Average value. Okay. So we're going to do average value here. So average temperature. Okay. What's the formula for average value? 1 over b minus a, depth integral from a to b of f of x. All right. So that's the formula. We can adapt this formula for our problem. What do you think our a and b values are? 0 and 15. Okay. Now, instead of f of x, I'm going to say w of t. Now, we don't have a WT function to find the depth integral, power rule, all that, but what we can do is we can use the data to approximate using trapezoids. So we're going to use trapezoids area to approximate what this region is going to represent. Now, you guys remember the area formula for a trapezoid? 1/2 base or 1/2 width. And then what? Times, yeah, height 1 plus height 2. Okay, it's a little tedious here because we have quite a bit of data here, but we have one trapezoid here, second trapezoid here, third trapezoid, fourth trapezoid, and fifth trapezoid. Okay, I'm going to use squiggly line to indicate that this is just an approximation. We're using trapezoids to figure out how much area is under this graph. So 1/2 width. What's the width of my first trapezoid? 3, right? In fact, all the widths will be what? Will be 3. Now, technically, we could factor that 1/2 width out and then just add up all the heights, but I'm going to write them all out just because in most problems, your width is not going to be the same. And I just want us to get into the habit of treating every region separately, even if there is a shortcut like in this one. I don't want us to get too comfortable with expecting the width to be the same. So it's a little more tedious, but we're just going to write it all out. Okay, but to save you some time here, I'm just going to tell us what the area is without you having to do all that. So it ends up adding up to 376.5. Okay, is this the average temperature? We still have to do what? Yeah, involve the width, right? And also, if you were here and you were trying to present this answer, this would kind of, there's a bit of a red flag here, right? You look at the temperatures here, they're all in the 20s and low 30s, and all of a sudden your average temperature is 376. It's not quite making sense, right? So that helps. Hopefully that will remind you, oh, I still got to involve that width component in order to get it down to the average temperature. Okay. And looking at these temperatures, we should be getting something in between 20 and 30 degrees, right? Somewhere in that range. Our lowest is 20, our highest is 30. So our average is probably somewhere between 20 and 31. Okay. So it ends up being 25.1 degrees Celsius. Oh, and then squiggly line, because, I mean, we don't know the exact average temperature. We don't have our data is so spread out that this is the best we can produce based off of the restrictions that they're giving us. Oh, the bounds, well, once we get into trapezoid approximation, this number is going to replace this whole expression. We don't have to do any power rule, anything like that, because this is just an approximation. So it's going to fully replace this entire notation. But yeah, if we had a function to work with, then we would involve the bounds and power rule or whatever the integral notation is to get there. Okay, part C, a student proposes a function P given by P of T as a model for the temperature of the water in pond time T, where T is measured in days and P of T is measured in degrees Celsius. Find P prime of 12. So now we're doing the same thing as part A, but with more accuracy. So now, you know, before we're forced to use a table of values to approximate using algebra, and now we can use calculus to find potentially a better rate of change on the 12th day using P of T, because this is now going to model the change in temperature at much more accurate terms. So to find P prime of 12, we can just find the what of P of T derivative, right? And then evaluate the derivative at 12. Okay, so we can use our calculator. The Math 8 feature can help us get there, right? We don't have to do this by hand. The calculator will will evaluate the derivative for us. Again, we want to use what variable in the calculator? X. Yeah. So I'm going to go to Y1 again, just so that now you don't have to do this. It's just if if we're calling the same function multiple times, it's just nice to not have to type in everything multiple times as well. So I'm going to type this in here, 20 plus 10x under y1. E is under well, second for natural log. You see natural log above natural log of E, so do second natural log to get that exponential function to show up. And then parentheses, negative t over 3. All right. Once you're there, then do second mode. Second mode will take you back to your home screen. And now we're going to do math, what? Math and deriv, right? So math 8. Alpha trace will get you to your y1, which is now holding your p of t function at x equals 12. So it's going to find the derivative at the 12th day for p of x. What's our unit of measure? Yeah. So it's basically supposedly a more accurate version of part A. Okay? They're both describing the same things. It's just that here we're using limited data, and here we're using a function's derivative. So we can tell that they're in the same universe, right? They're talking about this. This is an approximation. This is an exact value, but still describing the same thing. On the 12th day, the temperature is decreasing at that rate. Okay. Part D, use the function in part C to find the average value over the time interval between 0 and 15 days. So again, we're going to use what? Average value theorem. So we're approaching part B. We're approaching part D with the same formula, but with a different method, right? So part B is using approximation with geometric shapes. Now we can find potentially a better average value using our P of T. So instead of W of T, where we're looking at the area underneath using trapezoids, now we can find the area under a curve, and this is potentially more accurate. But now we can use, this will require a calculator, right? Now we can use that Math 9 feature to actually do that, find the area under the curve for us. But B and D are both trying to answer the same question, just from a different starting point or different method. Okay, so Math 9. From 0 to 15. You can type that 1/15 in front if you like. I'm just going to type this in and then divide by 15 at the end. So 386 divided by 15 gives me 25.757. So you can see that, part B and D are, describing the same things, and their answers should be pretty close. This is an approximation. This is supposedly an exact average temperature, according to the model. It's supposed to be a better accurate solution. Okay, page 2. Right. Only 3 questions. So we 1 and 2 are referring to kind of, well, number 1 is particle motion. Number 2 is, this is Riemann sums. And number 3 is a derivative graph. So this one, number 3 here. Yeah, you can use calculator for all of these. But some problems like this one, the calculator is not as, we're not going to use it as much. It's not as useful, but yeah, you get to use the calculator for all 3 problems. Okay, it says the graph of the function is shown to the right, consists of a semicircle and 3 line segments. Let g of t be given by, or g of x given by the integral from -3 to x of f of t. So if I want to find g of x, is the area under my f graph. And this is my f graph, so I'm going to say f here. So I'm going to box this off because we're going to definitely use this. G is defined as the integral from -3 to x. And then part A says find g prime and g double prime. Okay. So g prime means I want to find the derivative of this integral. All right, what does this remind you of? Derivative and integral next to each other. This is second theorem, right? Remember second theorem? So second theorem says, okay, if I'm doing a derivative integral, that means they're going to wipe each other out. Another way to think about this is that right now, this g of x is sitting at 1 level above f. So g prime will bring us back down to f, right? So we know these 2 operations cancel each other out. Upper bound into the function. So f of what? F of x times 1. Okay, so I'm gonna leave that times 1 out because it's not going to mean anything. But basically, g prime is the f. Now, this is the f function. So I want to say equal to g prime. So this is the derivative graph of g. Okay? And because we're looking at the derivative graph of g, we have to think back on first semester in a little bit, right? So above and below the x-axis, all that. Okay, so this is a derivative graph essentially. So if g prime is f, then what do you think g double prime is in terms of f? F prime, right? So basically, f and g are kind of staggered, right? So we're just making both go down up or go down 1 level. Right? So g prime is the f function. So basically, this is my g prime graph, and g double prime is my f prime graph. All right. Now we have 3 functions available to us to help answer any question that they're asking us to find. Okay. So we're going to, anything that we're asking for, we're going to go back to these definitions that we've established. So if I want to find g of 0, which definition do I want to use? The first one. Right? So g of 0 means I'm going to replace every x with what? The 0. So let's do that. We have a graph in front of us, so the definite integral from -3 of f of t dt just means that we're going to find the what between the graph, or involve the what? Area. Okay. Except what's below the x-axis, we got to count as what? Negative. So the first thing I want us to do is let's just make sure that we know what region we're talking about, because we have all these shapes that we can see, but if we don't realize what region we're talking about, then we're maybe potentially adding the wrong area. We're only looking at the region where? Between the graph and the x-axis. So anything else is not part of our graph. So let's just start off by doing that. We got to know what region we're looking at. So just lightly shade in what you see between the graph and the x-axis, because that's the only thing we care about. Anything, I know you may see a semicircle, like a semicircle here, but It's actually only what's between the graph and the x-axis. Okay, it's asking for between -3 and 0. So between -3 and 0. Right, what shape do you see there? Yeah, trapezoid. We can do trapezoid area formula, or if you want to prefer to use other shapes, we can also split this trapezoid into what? Triangle and a rectangle, right? So maybe if that's easier for you, you can do that. So you can find the area of the triangle, find the area of the rectangle, add them up. And that will represent what we're talking about here. So 1/2 base times height is 3. Length times width is 3. So 4.5. Okay, G prime of 0. Okay, do we have something defined using for G prime? Yeah. No, something else. What do we do from part A here? But you're right, the graph. G prime of x is equal to f of x, so therefore G prime of 0 equals what? F of 0. Well, what's f of 0? How do we find f of 0? We look at the y value of the graph, right? This is the f graph here. So what's f of 0? 1, yep. So if we can have these definitions spelled out correctly, then we just have to follow whatever the definition tells us. Okay. Next up, G double prime of -1. G double prime of -1, we have this defined here as what? F prime of -1. So I'm going to highlight -1 on the graph here. What is f prime of -1 asking us to find for this? The slope, right? It's asking for the rate of change or the slope. The derivative, yes, it's derivative, but it's a nice straight line, which we can find using algebra, right? So slope is what? Change in whatever change in x. So if I can find the slope of this line segment, I can find the slope at that point. Okay. So slope of this line segment is what? Down 1 over, yeah, so -1 over 3, right? Rise over run, down 1 over -3. Okay, any questions? Okay, we still have to do part C and D, but we can do that tomorrow. But it's good. We got through 2.5 questions. We're just going to go through the same 3 problems, same 3 types of problems tomorrow. We'll do some more on Wednesday. We'll do some more on Thursday, and then Friday text. Okay, come get your phones. Right. But there's still some variations we got to get through, but basically, yes. It'll be 100 points as well.
We don't have to do anything in a hurry.
No.
It's like-